Hi, my name is Pedro. I'm a staff engineer at SRS. I've been working with SRS since late 2017. I work mostly in the upper layers, anything from RLC and above I've dabbled in. And I'm going to talk to you a little about, and in the last while I've been working mostly on the user plane part of the protocol. And from that perspective, I'm going to talk to you a little bit about debugging TCP streams with srsGNB. So who here has had this problem that you have your GNB set up, you have full UDP stream. So I see at least one person, great. You have a full UDP stream, and then when you run TCP, you have half the bandwidth. You have 2/3 of the bandwidth for, and you don't understand. The channel is good. What's happening here? So that's kind of like what I'll try to address in this talk. This will be a beginner's talk. Like there'll be no need for specific TCP knowledge. I'll walk you through a little bit of the TCP protocol. I'll try to be quick. I believe we all know more or less. Then I'll discuss logs and PCAPs that you need to get to narrow down what is the problem and how to interpret it. And then finally, I'll get to the what are common issues that are happening when this is the case. So just to start off, just so we're all in the same page and we have all the same terminology. So TCP is a stream protocol. Each PDU is called a segment. Each segment has a sequence number. The sequence what I want to emphasize here is that sequence numbers are bytes, not PDUs. So that's different from RLC, PDCP, GTPU. So that's important that we all are clear when we're talking about TCP sequence numbers. It's bytes, all bytes. So it will implement reliable transport. All bytes have to be ACT. If there is a gap in the received sequence numbers, there will be a duplicate ACK sent. So when we're debugging, that's one of the things we're looking for duplicate ACKs. And also retransmission timeouts are also used to detect losses. And TCP will implement congestion control. This is kind of the root of all problems. So there'll be two state variables. They'll be kept, the congestion window and the receive window. The congestion window is a sender side limit on the bytes in flight, and the receive window is a receive side limit on the bytes in flight. And bytes in flight are the bytes that have been sent but not yet ACKed. So this is a very important thing to keep track when you're analyzing your connection. So just so this is a plot of the bytes in flight. You can get this from Wireshark, and you can see the slow start of the TCP connection, where it grows very rapidly until a congestion is detected. You drop your bytes in flight and then slowly build up again, and you drop again the bytes in flight. So when you have this issue of a TCP problem, this is what you want to look for. So where did the loss happen and why did it happen? So again, if you receive 3 duplicate ACKs, you will detect the loss. If you do not receive an ACK within the retransmission timeout, you also detect a loss, and your congestion window gets dramatically reduced. So losses are the problem. Losses are what you really want to find. But if if you're using oral CAM, you have retransmissions. So why would there be losses? right? And you should be using RLCAM during TCP streams. You don't want packets being lost in the air interface. So why are there losses? And there are many places that there can be losses that are not the air interface. And we'll discuss a little bit later on more about this. But before, let's talk a little bit about what kind of logs and PCAPs you should be getting if you want to get to the bottom of the problem. So the first thing to get is a TCP dump at the entry interface, so at the interface that the GNB is receiving. This will let you see, are the packets even reaching the GNB? Or are they being lost inside the GNB? Are they being, so this, or inside or after the GNB? So this is one of the easiest ways of getting some information. We also implemented a configuration variable called the warn on drop, so that if there is a drop somewhere inside the GNB, you will be warned. There'll be a log entry so that you can later inspect and figure out why was there a loss. You can, and another good way of using this is to look at the PDCP and RLC metrics. They will tell you if you have losses. We don't have GTPU and F1U, N3 and F1U metrics yet. This is something that we want to add, and should also simplify, okay, where am I getting excessive losses? And finally, after all these, you can look at the MAC PCAPs. But the MAC PCAPs, they have a performance overhead, so I try to, they're kind of a, you really want to narrow down what's going on. And then if you can, PCAPs at the UE and the UPF are always useful because they're the transmitters of the connection, right? So that's always good, but you don't always have the ability to do that. So if you can, that's also good. Finally, try to get the start of the connection. There are important information exchange at the beginning of the connection that Wireshark will use to interpret, to generate, to do some of its plots. So try to get that if you can. No need for long captures unless your problem takes very long to manifest. Try to get short, save your disk space, and also no need for full packets. There is an option in TCP dump. Capture only the headers. You don't need the payload. Unless you specifically need the payload, don't capture it. Save your disk space. Save yourself the bother. So once you have that, what do you look for? What I usually start is just Wireshark's expert information. It will tell you, for example, this is a capture at the entry of one time we were having issues, we're having losses, and Wireshark will tell you exactly previous segment not captured. You can go there and figure out, okay, I didn't receive this segment. Why? Why did I not receive this segment? And you can try to like narrow it down further. After looking at this, Wireshark has very useful plots. I recommend that you have a look at them. The Drupal plot is not very useful. I mean, it's good, you see it, but it's not, doesn't give you that much information. But it's good to have a look, see what's going on. The RTT plot will give you the plot of the RTT over time. This can be useful if you have something like excessive buffering and the RTT keeps growing. But also what I find most useful are the window scaling plots and the TCP trace plots over there. So the window scaling plots are very interesting because they have the bytes in flight. And just by looking at them, you can immediately see where the loss was, right? And then you can click on the where the loss was, and Wireshark will go to the packet, and now you know which packet was lost. You can try to figure it out. And you can try to figure out why was it lost inside the GNB? Was it lost outside of the GNB? what happened. Finally, just a mention of this plot is also very interesting, the time sequence, the TCP trace. This will have so the brown line will be the ACKs, so the lowest ascent that has been ACKed. The white line is the receive window. The blue, the sequence numbers as they grow. And also, you can see here there was a loss. There's some selective ACKs. There are some retransmissions of sequence numbers that were sent again. So all these plots are very good for you to figure out what's going on, where are my losses, why is this not working properly. So finally, just some tips and tricks. I recommend that you use profiles. Wireshark profiles are great. You can put different columns so that you can change around quickly, and you can use filters to try to narrow down just show the information of what are the problematic packets. But that's it for that. So now let's get to what are the issues that we encounter sometimes. So, like I was saying, if you use oral CAM, there will be no oral CSDU losses, right? So the oral C will guarantee that in the air interface, there's no losses. But that doesn't mean that there are no losses anywhere else. There can be losses before the core. There can be losses between the core and the GNB. There can be losses inside the GNB, and even at the reception, at the UE, and after it. Not all are equally likely. Some things are more likely than others, but these are all potential loss points that you need to watch out for. And the reason for all these losses can be bad buffer configuration. Your buffer is too small. You drop at because your oral C buffer is too small, you drop inside the GNB. If your GTPU buffer is too small, you might drop at the GTPU. Maybe you don't have enough processing power and the kernel can't deliver packets fast enough to the GNB. There are many things that can go wrong. So let's try to walk through some of these common issues that we have encountered in separate issues. So one thing is the TON interface. Some cores implement and some software UEs as well, implement their interface as a TON. The default queue size parameter of the TON is not that big, 500 packets. We have had 2 instances within our company where we spotted this problem, where the core was not reading fast enough, and we had also one user at least who also have this instance of the core just not reading fast enough, and we were having drops in the TON, and it was affecting the TCP. It was affecting the TCP throughput. You can check for drops using the IP command, and it's very easy to just increase. If this is happening, it's a very simple solution. Just increase the queue a bit. Usually, you don't need much more than that, and you simply resolve a hard to spot, easy to fix issue. Then losses at the entry. So losses at the reception of the GNB. Here, the most common culprit, at least in our experience, is the NIC queue. So the NICs have a queue inside them, which is not always defaulted to its maximum value. So you should check for so if you use the ethtool command, you can check for statistics of how many drops is your NIC having. And if you are having drops at the NIC queue, you can simply increase it. This resolved, this is a fairly common problem, that it's also a fairly easy fix. But the entry has a lot of potential for drops, so that's not the only one. There is also the kernel itself not having enough processing power to process all the packets. So once the kernel has received the packet, it will raise a soft IRQ to do the actual processing. It will put that in a backlog queue, and the software queue itself has a budget for how long it can process the packets. So if you can check, by catting that file there, you can check for drops in the backlog queue, and you can check if the processing budget has been exceeded. So the drops you see there in the second column, and the processing exceeded is there in the squeeze column, and you can see it for each core. So okay, but so something's going wrong. What can I do? And this is a harder problem, but what I recommend is check your IP tables. Sometimes if you have a lot of IP tables configured, they might be, if they're not well configured, they might be doing excessive processing and causing the packet not to be processed in time, causing lack of resources for packet processing. Another thing that you can check is, are there other threads running on the same CPU as the soft IRQ? So is the core under stress because of other things running there? So this is a screenshot from an issue we had where we had too many threads in the G-Node B, and the core that was doing the actual reception, you can see there it's at 80%. It was, this wasn't that screenshot, but it was even jumping to 90%. If you see something like that, you should try to figure out, can we avoid this? Can we, or what's causing this? And if that's neither of those are the problems, you can always try to increase the backlog queue or the processing budget, right, to give it a bit more room to breathe. So continuing the entry, that's not there's still the UDP buffers, right? So check your UDP buffers. Are you getting drops because of UDP buffers being full? Because the GTPU uses UDP. So if you're pushing too much traffic to the UDP buffers, you may get losses. And finally, to finalize the entry, UDP does not guarantee any ordering. So you can get reordering at the entry. It shouldn't happen a lot in a normal situation, but we have seen it. One of the reasons we've seen it was when the MTU was poorly configured. There was IP fragmentation going on, and packets were arriving out of order because of that. So try to, and remember, out of order to TCP is the same as a loss, as in it will send a duplicate ACK anyway, and the transmitter will act as if it was a loss, even if it isn't. So for that, try to make sure you don't have reordering. And if you can't get rid of it, there is a feature in some cores. It's an optional feature, so not all cores support it, but some cores support sequence numbers, GTPU sequence numbers. So if you can enable that, because on our G-Node B, we implemented a GTPU reordering timer. So if you get out of order packets, the GTPU can reorder them as long as you have GTPU sequence numbers. And you can, if you use the warn on drop option, it will tell you if you had drops, because and if you receive out of order sequence numbers. Moving on from the entry, now inside the GNB. The GNB has queues inside it, right? And those queues can fill up. So this is considering the downlink. When you receive a packet from the UDP, it will come through the GTPU demux, and it's put into a queue at the GTPU tunnel RX for later processing. This queue can fill up. So you have to watch out whether this queue is filling up, or if it's too big. If it's too big, it can also cause problems. So you have to watch out for this queue. It's the first barrier of entry to the stack. So try to see, am I having excessive losses because of this, or not? And then later on, also the RLC has a queue. The RLC has a queue because the way it works, the GNB, is the PDCP will push packets into the RLC, and then the RLC will wait for the MAC to pull them, right? So the queue is the interface, right? So the losses won't be so if you fill up the RLC queue, the losses won't be in the RLC. Actually, this is because of the way 3GPP has done things. So they will be actually in the PDCP. The PDCP will know how big that queue is, so to drop early, because a loss in the PDCP sequence number implies a delay at the UE, because of PDCP is responsible for in order delivery. So a loss in you really don't want to lose a PDCP sequence number if you can. So there is some mechanisms to avoid that, so that you know that the PDCP knows the size of the RLC queue and will drop early, right? So again, you can check for this using the warn on drop, and also this one will be logged in the metrics, so you should do that too. There's one other queue that I failed to mention here, which is also in the F1U when transitioning from the CUUP execution context to the DU. There's another queue you can also drop there. So as you can see, there's many drop points, and this is for the downlink. It's very similar to the uplink. There's some queues also at the end of the GTPU tunnel, and then the transition from the MAC to the RLC. So if you do have losses there, what can you do? And there are configuration options for all the buffers. You might have to do some fine tuning for your specific use case, but I'd say have a look at these, see if they help your case or not. Remember, making them too big can hurt performance too, so be careful. It's a bit of trial and error, but do have some trial and error. And okay, and finally, losses at the PDCP RX, so on the UE side. This is not as, if your channel is decent, this is not so common, but for the sake of completeness, I included here as well. So the PDCP is responsible for in-order reception. For that, it uses the reordering timer. That means if your PDU arrives at the PDCP on the other side too late, it will be dropped. But how do you know that? That's kind of hard to know. How much time did it take to arrive on the other side? And the best inference that I have is the RLC metrics. You have an ACK latency. So you can know how long it took for a PDU to be ACKed. So you can look at that and see, okay, my ACK latency on the max was 33 milliseconds, but my reordering timing is 100 milliseconds or 200. So it should be good, right? So this shouldn't be a problem. But that's the best that you have to detect these kind of losses. Again, this is not usually the problem, but it's still good to know. And also gives you a good idea of what your RTT is in no load conditions, right? So that you know if you have extra, it's not because of the air interface. And finally, a little bit about the actual TCP buffers. The TCP buffers are not related to the GNB. The TCP buffers are between the UE and the core, or more accurately, between the applications on the side of the UE and the core, right? So this is something that you shouldn't control, but if you're running a test yourself, you should be aware, right? So if you have control of all the variables, you should be aware of this. And basically, if you send all the, if you fill up your buffer before you get an ACK, the TCP will stall, right? So if you fill up all your receive window or all your congestion window before you get an ACK, it will stall. So you should calculate your bandwidth delay product and check, do I need to increase these buffers? The receive window is very easy to see because Wireshark will plot here in green you can see the receive window, the size of the receive window. So as you can see, the bytes in flight are there touching the receive window. It's very easy to see. That's the problem. The congestion window is a bit more tricky. But this is what you should do if there is a problem here. And I think that's it from my side. Just some references. If you are in any way dealing with these sort of problems, or I strongly recommend that you read the Tuning Network Performance by Red Hat. It's a wonderful guide that will walk you through a lot of the problems that you see more at the NIC level, at the N3. And if you have more interest in TCP, the RFCs are great resources. And that's kind of it from my side. If you have questions, please. Yes.
Question. So you mentioned about the entry the queuing there. From the perspective of deploying srsRAN on DPDK mode, is there any specific setting that you need to do using, let's say, ETH2?
But
take into account, let's say, for example, checks.
You're talking about DPDK, but we do not use DPDK at the N3. So the N3, at the moment at least, it has no option to use DPDK. DPDK is only used in the OFH interface, so in the split. So at the moment at least, there is no way of using DPDK. Yeah. Any more? Yes.
Turn on the warn on drop. Is that just something you turn on as a configuration?
Yes, that's just a configuration option. It's in one of the GNB options. I think it's in the root part of the configuration. I'm not entirely sure right now where it is exactly, but I can show you later if you want. But it's one of the options. It's called warn on drop, and will tell you whether there's drops. Metrics are a bit better way of looking at this, but not all layers have metrics yet. So the warn on drop can be a bit spammy because for every drop we will get a login. So we're improving the metrics, but still the warn on drop is the most complete at the moment. Yes.
Okay, I think we do have time for one more question, and then
okay.
So my question was about the window scaling plots in Wireshark. Maybe just because the text was a little bit small, I was having a hard time reading one of the axes, but show like more specifically the spikes there would indicate a lot of X. Or
no, this is the bytes in flight, right? So it means that it's still transmitting until like it finally.
So that's the time range you want to look closer into.
Sorry. Yes. Exactly. Yeah. So here you can see the bytes in flight dramatically drop, right?
Why do they spike up so much right before they drop like that?
I believe, and I may be incorrect, is that you're allowed to increase your congestion window for each duplicate ACK. So allows you to transmit a bit more while you're still getting lots of duplicate ACKs. I'm not entirely correct. I'm not entirely sure, but that's my belief. So I may be incorrect. So just take take the answer for what it is.